Michael, Physics 2211, Lab 3. Brief overview of the contents. 1 will have introduction, 2 models, data, and observations, 3 code, and 4 discussions. The purpose of the lab is to create the trajectory of a unique star by using net force, velocity, and mass. The fundamental principle observed here is Newton's second law. A brief preview of what we found, or what I found, through the use of unique glow script code. The black hole's mass can be found, which helps to then calculate net force and initial velocity. Newton's second law, the primary physical concept at play here. Newton's second law, known as the momentum principle, states that the force is equal to the change in momentum over time, as shown in the bottom formula. It indicates changes of movement within the system and the surroundings. This principle will be in use when trying to calculate the forces on a star and how this influences the initial velocity of a spaceship. A brief procedure, part 1. Analyze the motion of a unique star through glow script code to find the net force and calculate the mass of the black hole, assuming the net force is due to only the black hole. Part 2. Use the mass of the black hole that is found in part 1 to calculate all the forces on the planet and all the forces on the spaceship. Use glow script to find the initial velocity necessary for the spaceship to avoid being sucked into the black hole. Initial values: position of the black hole at the origin, 000. Mass of the star, 2 times 10 to the 30th. And mass of the black hole is initially unknown. GT email was initially added to the top of the code. It can be assumed that there are no external forces acting on the system. This is also the extent of the observation made, since the rest of the experiment is entirely code-based. System versus surrounding. Well, the system in part 1 is the star, and in part 2 the spaceship. The surroundings in part 1 is the black hole, and in part 2 is the black hole and the planet. And here is my code. So some changes I made from the starter code. I changed the mass of the star, initial and final momentum, change in velocity / momentum in the code, average change in momentum, change the net force, the components of net force, parallel and perpendicular, and calculate the mass of a black hole. And the changes also, arrow scales and GT-EML was put in for seed. The first figure represents the mass of the black hole based on how the net force changed per day. The coded model showed the direction of the forces while the star orbited the black hole, as you can see in the figures to the right. The mass of the black hole was found by using the normal gravitational force equation and isolating the black hole mass. Once the code ran and gave all the varying mass values, I used Excel to calculate an average for the 443 days, finding that the mass of the black hole was equal to 1.15 times 10 to the 44 kilograms. Part 2 of the code. Changes I made to starter code. Mass of black hole, which I found in part 1. Planet speed, ship speed in X and Y components. Net force on the planet, net force on the ship, and the movement of the spaceship and the planet. And this is a figure I got using the new code. This model was produced showing the ship, the pink line, moving right around the black hole with the planet, the blue line, helping pull it away. Potential error. Since there is no tangible experiment here, there is little room for error. However, it is possible that a value was incorrectly calculated due to a mistyped formula or something of this sort. Discussion. So what does this mean? Net force, parallel, and perpendicular in this case is numerically the same as the change in momentum, parallel, and perpendicular. The difference, however, is that net force is the sum of all forces acting on the object, while change in momentum comes down to the change in the motion of the object. And what if? To find the initial velocity of the ship to follow an orbit around a black hole, I used trial and error to find what speed the ship would need to be. This came out to be around negative 8.14 times 10 to the 13th in the x direction and 4.81 times 10 to the 11th in the y direction, meters per second. That's the end of my presentation. Thank you, and bye.